Hi there, welcome to this video about the A-level physics required practical into diffraction. So diffraction proves the wave-like nature of light, but for this practical the aim is to determine an actual value for the wavelength of different colours of light using diffraction. There are two versions to it, or your school might get you to do both. One is using the double slit arrangement, and the second one is to use a diffraction grating. We're going to look at each of them in turn, and I'll talk through what the method is, how you can find the wavelength, and significant errors and safety issues with the practical. So in the setup I'm drawing down here, we start off with a laser. Now often you'll have to shine it through a single slit first before it goes through a double slit. On the screen you'll see a pattern of light and dark fringes, which are as a result of the wave superposing, which means there's positive, constructive interference and destructive interference. The single slit is there to ensure the light going through the double slit is coherent. That means it's got the same frequency and it's got a constant phase difference. If you're shining your laser quite close to the double slit so that the whole laser covers both double slits, you are likely to find you won't need the single slit anyway. It's just to ensure that. And this is what Thomas Young did in his original experiment back in the 1800s. So the equation we're investigating or using to investigate the wavelength is this one here. W equals lambda d over s. W here is the width between the bright fringes as I'm drawing on the diagram. D is the distance between the double slit and the screen, so not between the laser and the double slit, but the double slit and the screen. And obviously wavelength is going to be the thing we're investigating. S is the double slit distance, so the distance between each of the slits. There's two versions to this version of the practical. We can vary the distance between the slits and the screen and then measure the width of the fringes, or we could vary S, the distance between the double slits, and then measure the width of the fringes as well. Both of the methods are in a similar way, it's just how we do the write-up at the end that is the difference. So this practical, you're likely to need a couple of clamp stands and clamps, one to clamp the laser in place, another to clamp the double slit or maybe the single slit as well in place so that it can be lined up perfectly so that the laser light is exactly perpendicular to the slit. If you're just doing it by hand, it's very hard to make sure that's consistent every time. So let's have a look at the method then. So we're going to set up the apparatus first of all, and we're going to say the distance from the double slit to the screen, D, is 1 meter. Next, what we're going to do is use a ruler to measure the width of 10 bright fringes on the screen. We're then going to divide by 10 to obtain W, or a mean value for W, the width of the fringes. The reason we do this is because it's more accurate, as the width of the fringes will in reality only be maybe a few millimeters, if that. So if your resolution on your ruler is plus or minus 1 millimeter, you've got quite a high percentage uncertainty if you just measure 1. Because you're measuring 10, that's likely to be a fair few centimeters, so you're improving the accuracy. We're then going to vary the distance between the slits and the screen by about 10 centimeters, then repeat these steps and gain values for at least 7 or 8 values of D. We're then going to record the slit separation, which is a constant, and that should be on the slits which you've got. If you've manufactured, are very likely to give you that value on there. If it's not on there, you could use a vernier caliper to measure the distance between the center of those slits anyway. Let's talk about errors with this practical, or things we can do to minimize them. So we are measuring, as we mentioned, multiple fringes to ensure that this is as accurate as possible. We're going to make sure the light hits the slits perpendicular or normal to them to ensure that all of it goes through and to ensure it's all coherent. And we are going to try and keep X constant. So in this case, X is going to be the distance between the laser and the single slit. It shouldn't make loads of difference, but it could be that there's some diffraction occurs before the laser gets to the single slit. So we want to minimize that effect if possible. So what we could do is just use the calculation to work out a value for wavelength and then maybe go again and try again with a different color of light. However, because we've taken lots of different measurements, it's a really good idea to draw a graph, and it's good graph practice in A-level physics. So on the graph, what we'd have, if we vary D, so that would go on our x-axis, and we measure W, we could have a straight line graph. Those two things should be directly proportional because the wavelength and the slit separation is constant. The gradient of this graph would give us W over D. Where if we rearrange this equation, so W equals lambda D over S, we could rearrange it for lambda, meaning it's given by W over D times S. W over D is our gradient, so therefore to find our wavelength, we would then multiply the gradient by the slit separation, and that would be our value for wavelength. Depending on the color of laser you're using, obviously we should know it's a known value, so you could compare it to a known value. So for example, for red light, talking about 700, 650, 700 nanometers. And then for violet light, you're talking about 400 nanometers. If you were varying something slightly different, so you could be varying the slit separation if you had multiple slits with known slit separation, we have to plot the axis slightly differently. Now, W and S are inversely proportional. That means if one doubles, the other halves. They're not directly proportional here. So what that means is we can't just plot W and S on our graph because our gradient wouldn't give us anything. So we can plot W versus 1 over S. Now, W over 1 over S is the same thing as WS. So therefore, our gradient is going to be equal to the width of the fringes times by the slit separation. From our equation from earlier, we can then rewrite that to say if we wanted to find our value for wavelength, we need to do W over 1 over S. That gives us WS. And we need to then divide by D, which is going to be the distance between the double slit and the screen, which is constant. Okay, let's talk about a very important part of this practical, which is about safety. This applies for both methods, and it's all to do with using lasers. Now, obviously, lasers can damage your eyes and your retinas. So what we're going to make sure is in any lab we're doing it, we try and remove as many reflective surfaces as possible and don't do our experiment near them. Take them off the walls if there's any shiny laminated posters or something like that. We're also going to avoid looking into the beam. I wouldn't say things like don't shine in people's eyes because that's kind of obvious. But for example, when you're doing the experiment, have your back to the laser if it's on and you're taking a measurement. You can also get laser safety goggles. However, your school's unlikely to have those because they're very expensive. So these are the more obvious precautions you could take when using lasers in a school. So that's the double slit method for finding the wavelength. Next, let's look at how you could use a diffraction grating to find out the same thing. Now, with a diffraction grating, we're still demonstrating diffraction. It's still the same effect occurring. However, a diffraction grating has many, many slits. Often you'll find it's got hundreds of lines per millimeter. And diffraction is going to manifest itself in a slightly different way, as when you've got a screen and you've passed the laser through the diffraction grating, you're not going to have an evenly spread interference pattern of bright and dark fringes. You're going to have slightly more separated, distinct spots called orders, which are bright spots and then a gap between them. So let's have a look at what the diagram looks like and the equation. In this experiment, you could use a single slit to make sure the source is coherent. Again, I haven't drawn it in here, but the light goes through the diffraction grating and it hits the screen on the other side. There's a distance, capital D, between the diffraction grating and the screen. And this time, instead of just looking at the bright and dark fringes, we're calling them orders. And the central one is called the 0th order, or n equals 0. And in either side to that, they're called the first order, second order, third order, and so on. We also need to be aware of the angle that the beam makes with the central order, or the 0th order. The angle is theta here, and we are going to have to calculate that. You can't use a protractor to do that because it's a very small angle, and it's going to be very difficult to measure that directly. The last thing to look at is the n, which is the number of orders, and this equation applies here, this diffraction grating equation, which is n theta equals d sine theta, where little d, so not capital D, is the spacing between the gratings. I'll show you how to calculate that later. If you want more information on where that formula comes from, check out my video about diffraction. So let's have a look at our method then. So we're first going to set up the apparatus so that D is constant. We're not going to change that here. Then we're going to measure the distance between our 0th order and our first order using a ruler. I would do it twice, do one either side of it, and then find a mean. Next, we've got to find what theta is. So to find what theta is, we've got to do a bit of trigonometry. We use that distance between the 0th and the first order. That's going to be our opposite on our right angle triangle. Then we can also know the capital D distance between the grating and the screen, which should be constant. And then we can use tan theta equals x over d, or theta equals inverse tan x over d to find theta. Then we're going to calculate d using d equals 1 over capital N, which is the number of lines per meter. That should be given to you on your diffraction grating, but it will give you the number of lines per millimeter, so you have to convert that in meters and then do 1 divided by it. Then we calculate the wavelength using this equation here. Now we've used the first order here, so n just equals 1. You could do it for the second, third, fourth order, and in reality for this experiment, you're unlikely to get that many orders on the screen. However, if you were able to get multiple orders, here's how you could do it using a graph. You could plot the number of orders n on the x-axis, you could plot sine theta on the y-axis, and the wavelength would be found by finding the gradient, sine theta over n, multiplied by d, which is a constant, which is the spacing between the gratings. For this experiment, you could use different wavelengths. You could use a red laser, green laser, purple laser, violet laser to find what the overall, what different values are for wavelength. Again, it's a known value, so look it up and find a percentage difference between them. So there we go. There's the experiment for diffraction and calculating wavelength using double slit and diffraction grating. Hope you found that useful. Please leave it a like and check out my other A-level videos for physics.